Okay, good afternoon, everyone. Thank you to the viewers who will watch this pre-recorded webinar. We're here today for another webinar in the CARSI series, and this time we are joined with an international guest, Josh Woolen from EGA-Commissioner, which is based in Pennsylvania in the States. He will be speaking to us about vapor pressure. Josh, you've got a presentation you will talk through, I understand, and you are happy for any viewers to reach out to you with questions following the webinar release. Thank you. So if you would like to introduce yourself and take it from there. Thanks, Josh.
Sure. I'm Josh Woolen, and I've been working with the disaster services for about just over 30 years now. So got a little bit of an insight from doing the disaster work myself to being a consultant to being an environmentalist and also being one that sits across from the contractor and was that enemy of the contractors. And now I'm blessed to have the knowledge that I can leverage things for the contractor and help them keep what they've done. So with that, I'd like to do is introduce this presentation. The presentation is about the key metrics in building science and the drying performance. And we'll refer to that as water vapor pressure. And we'll start from there. So for the most part, for all of us, we all understand that water has a molecule that vibrates. And that energy is carried, therefore, we can sense it as it gets hotter, right? And when that liquid or solid water molecule evaporates fast enough, it can break the hydrogen bond, right? And this is a lot of science there with understanding vapor pressure. And it's all about the van der Waals force, and it becomes a gas. A vapor molecule assumes it's a vapor phase due to its energy carries. And releasing itself and transferring its energy to another substance. And understanding this can challenge many of us in our comfort in the knowledge of restorative drying, which is often nothing more than an observed restoration dry plan. We observe something from someone and we just think that's the way to do things. We don't challenge ourselves or challenge them to explain it to us. As such, vapor pressure should not be confused with a barometer pressure, right? The barometric pressure refers to the total force of all of the gas molecules colliding against the sides of the containing vessels, whereas vapor pressure, on the other hand, is precisely the measure of force exerted by the water vapor molecules, right? So during this time, as we move through this, engineers and contractors have designed buildings and build buildings to understand vapor pressure from the natural resources around all of us. And so it's very, very important for us to understand these things. So while we're exploring the vapor pressure and we talk about its pivotal role in structural drying process, from the environmental vapor pressure, which is the air itself and the forces exerted by the single gases within the mixture of materials that need to be drawn out. It's a lot, right? It's hard to explain even sometimes when you know how to explain it and you can simplify it, right? So to some people, we can go through and explain how vapor pressure is the basics. Vapor pressure in building materials, the engineering solution to optimum drying, and the pressure in building materials to equipment technology and interaction session with Q&A. So if that's good for everyone, and hopefully I've not scared anybody away We'll go ahead and get it going. When we talk about section 1, we're talking about like the water is being chilled so that molecules have a slow movement, but it's enough to allow the molecules to interaction, become ice and stuff like that. And it's very important that we understand some of these processes, because we need to understand the phases of water, and it's not what we sometimes just think a simple thing, right? Because we need to understand that what ice is and how water plays and all of that stuff in vapor gas, right? So with that being said,
Sorry, Josh, I don't mean to interrupt. Sorry, I don't
yeah,
want you to lose your chain of thought. I know you
no,
have a PowerPoint presentation. I'm not sure if you have tried to share it on the screen. It's just not showing at the moment.
okay, I'm sorry.
But I know that's okay. I know you're talking through the PowerPoint. So I was just
Okay,
thinking, I'm not sure if
okay,
it's working for you, maybe.
okay. Let me see. Can you see that?
Yes, perfect. That's
Okay,
great. Thank you so much.
you're
I'll be
welcome.
able to see what you're talking to now. Thank
Yes.
you.
Okay.
No worries.
Should I
Thanks so
start
much.
over then?
No, that's okay. Keep going.
Okay,
Perfect. Thanks.
you're welcome. So with the forming and breaking of connections, you need to understand how these molecules work for us as the restorer, because it's unique for us, right? So we need to understand the phases of the H2O world, right? We know it's ice, we know it's liquid, and we know it's gas, or some people like to call vapor, right? And some people do refer to ice as a solid matter, and there's nothing wrong with that. Potato, potato. But water in its liquid phase is an understanding the behavior of water in its phase is crucial for us as cleaners and the restorers. I know a lot of people think that the cleaners don't really need to understand vapor pressure, but just think about what they're doing when they are doing carpet cleaning. And they're adding moisture to that environment that has a natural vapor pressure. And we're adding that. Just like in a disaster of loss where a pipe bursts and it adds water to that environment at different types of categories and conditions. And then the final thing is, of course, is the vapor, right? And the water vapor itself is a molecule phase in which moves vigorously enough to break its bond with all of the molecular structures and stuff like that. So, and that's, you know, how we are starting our project here. If it'll go. So in simplest format, to figure out how to figure out vapor pressure, just like this. It's a rather simple project. If you look at it, you know that your temperature is and stuff like that. But it's not that simple. It involves a lot more than that. But yes, you can go to your psychrometric chart and you can put in the temperature and put in your dew, and then that gives you your vapor pressure, right? So, but moving forward, vapor pressure is crucial in the materials that we are drying. Each and every piece of material has a unique drying. You cannot dry concrete the same as you would hardened wood or a piece of plywood or a drywall in place drying, or just cut it out and dry just the structure and be done with it, right? But we have to understand the moisture accumulation and the damage that will come with that. And most of the time, secondary damages are due to wood deviations where they could be cupped or buckled or shrunk and stuff like that. Or they can be a mold, right? So those are our common secondary issues that we have to be concerned about. So this is why when we come into dry, we're there to help the building dry itself and retain itself and go back to being what is normal, right? So we oftentimes will use the desiccant dehumidifiers or LGRs to help set up systems to create this vapor pressure differential so that we can start the drying of the materials and the assemblies and contents. Now, typically, one thing to note is that the carpet cleaners usually will bring fans along with them, snail fans or a box fan, and they'll set it up to help get that vapor pressure movement started right away. Now, when we talk about the amount of moisture in the materials and the surrounding air effects, the vapor pressure in a building, we have to compare it to something dry within that building. And if you're going to do that, you need to do is find an area within 10, 15 feet of the wet location and establish that as your dry point. That helps because it's close enough to the environment that it should give you the quantitative answer to what is dry or what is acceptably dry, right? And that's going to be your dry number for the rest of your materials that are within your wet environment. Now, moisture, structural damage due to moisture can be reduced as long as the cleaner and the restorer knows what they're doing and they're applying the science and the engineering methodologies that we learn as basic tools and we gain as we go to shows and we learn to talk to experts and we get taught things and stuff like that. In a wet building, the vapor pressure is significantly higher due to the excess moisture within the materials, not within the air. We are not paid to dry the air out. That there is nothing in the world that you can show that. What we are paid to do is dry out materials, the assemblies, the contents, all of that stuff so that the client can get their environment back or back to as close as they had it, and then they can redesign it or whatever they want to do at that point. Now, the role of vapor pressure in a building material is crucial for managing the moisture. And a lot of that, again, is to prevent wood from shrinking, twisting, buckling, and all the other things that go on with wood materials. And it doesn't matter. It could be a seal plate, a stud, a support beam across the top, as well as mold and bacteria in this environment that gives to malodors, right? Like basements and stuff, or crawl spaces, and many other spaces. But the key concept would be to keep the vapor pressure permeability in control so that you're addressing all of this diffusion of the vapor and the retarders to control this environment and make this environment what you need it to be. And then here's a short text. The vapor pressure is important in the building science as it influences the moisture movement through building materials. It measures using methods such as dynamic static manometers. Manometers are really interesting tools when they're maintained and they're quality manometers, right? And isotopic scopes. These are another high-tech scope or high-tech materials that we can use to help things. The units of measurements are typically within pascals or millimeters or mercury. And the vapor pressure is influenced by its temperature and its humidity. And understanding these relationships helps design buildings that manage moisture effectively in drying the process, right? So now the engineering solution for optimal drying, that's a tough one because we have 3 different versions of drying, right? We can do open drying, we can do closed drying, we can do a combination drying. And combination drying is not just opening up the window like many people believe and shutting down the dehues. It can use the HVAC system within the building to raise the temperature to a comfortable temperature that allows for the difference in the vapor pressure environmental air and the vapor pressure in materials to have a difference that causes the release of the moisture from the materials. So how can vapor pressure be effectively managed in different climates and in different structures? And the answer is that it really can't be, because every environment is unique, every environment is different, and the materials can change rather rapidly from one floor to the next floor based on how things are set up and what things are where. Like if you go into a bathroom, you have all tiles, so you're going to have a different vapor pressure than where you have break area and people are heating up soups and breakfasts and lunches or whatever. They will add that vapor pressure there, but the building is designed to understand that language of science, and it accommodates that vapor pressure within those bathrooms, within those break areas, within the work area. So you already got an asset to your services, right? And there's no sense that you don't bring it in and use it to your leverage. Now, one of the latest advancement in drying equipment and technology is the relationship to managing vapor pressure. When we go to commercial dry out schools and stuff like that, we get a very narrow script about vapor pressure and how it works and everything. Whereas I'm telling you is that vapor pressure is the key for drying. And it's the key to everything. People like Pat Moffat and Kim Larson and many others will tell you how vapor pressure works and its effect for us in this environment that we live in today. Vapor pressure considerations are integrated into a lot of things. The importance in the compliance with vapor pressure standards. The future trends of buildings are going to that direction. And that's where we need to start going. And we as an industry need to start understanding, right? What we need to do is talk about vapor pressure is built in by the engineers because there is a code and there's a requirement by international law, building requirements for putting in that vapor pressure from the earth, from the sun, and from the environmental air around that building, right? They have to take that into consideration, but they also have to build in that factor. Then the contractor has to take that same thing and they have to take the building codes, the IBC codes, and a few others, and then they have to make sure that the engineer built that into the standard of that building, but they also got to put in control measures to protect the materials that are brought to the site every day and are pending to be installed and put into the building so that they are not introducing a secondary environment to the built and stuff like that. Now, here's a version of the psychometric chart. And what I've done here is pretty much created a understanding into how the enthalpy and all of these other environments work to help us, right? And the real thing is how can vapor pressure be effectively managed in different climates and structures? We talked about this before. You can't, there's no way. It doesn't happen. But knowing how the cyclometric chart works and understanding the cyclometric chart is a key thing for us all, right? I mean, because we understand that the first half of the science-based drawing strategy is all about cyclometric, right? And we understand that the second half is all about moisture in the materials. Those two things right there are all part of cyclometric chart, right? The psychometric chart itself is often perceived as a complex scientific tool that initially was designed by Will Carrier with multiple rulers and stuff like that. And he came up with this thing that we know as a psychometric today. And it was designed for the individuals to evaluate the dry bulb and the wet bulb temperature and the evaporation of the environment based on how air conditioning units work within that environment. And if you think about those three principles and you think about how that applies to us, that's pretty much done deal with the cyclometric chart, right? And understanding it. But while it can be very overwhelming. At first glance, one can grasp the physical elements represented on a psychometric chart with careful study and understanding, but it needs somebody when you learn to look at a psychometric chart is what I'm getting at. If you don't know, ask. There's tons of people out there that will give you assistance in learning that. A lot of times it's your instructor from the IRCRC schools, your instructors for RRA, and many other people can give you that information, right? Now, earlier, a little bit ago, I talked about the first and second half of drying, right? When we're talking about vapor pressure and drying science and engineer, the first half of that science-based drying strategy I mentioned is all about psychometric, which is the study, the application, and the formulation and the presentation of a psychometric involved in understanding the physical laws and measuring the thermodynamic properties that affect air and water mixture. By no means is the psychometric chart a scientific thing. It's a mathematical formula thing. Indeed, it is a metric that measures the elements influencing the changes in air and water mixture, right? The other thing that I last said was the second half of science-based drying strategy. Moisture and materials. When you're trying to develop a science-based drying strategy, the restorative drying industry and the cleaners have an historical focus heavily on just the environmental conditions, just the air itself. And they feel that once they've got the air to a certain temperature and to a certain RH, that they are dry. Is that actually what we're paid to do? And I ask you that because it's not what you're paid to do. It is assumed that this is assuming that this is the effective way to evaporate the moisture, right? When in fact, we need to go to the vapor pressure and address the moisture within the materials, right? And that's one of the things that was beautiful about the psychometric chart. And you look at it, it is really a great thing. The only thing that when you go to elevation and you look at a psychometric chart for elevation, this is zeroed out at the sea land level. But if you go to a 10,000 level, the vapor pressure will move. That is I'm sorry, the grains per pound will move on you. And there's quite a bit of a difference. So you have to pay attention to that if you're trying to count in grains per pound at an elevation. You want to make sure that you're using the right metric chart if you're using paper and stuff like that. But everything else remains the same, doesn't change. So just something to think about during your time. This right here, I want to do is show you guys this is the capture of the narrow field of comfort for the human person inside of an environment. A lot of HVAC professionals, IHs, CIHs all refer to it as the third skin, right? It's the example of how narrow the human field is in a comfort zone. I just take a look at that. That's why oftentimes you'll see a bed is high and it's at that level of being 65, but with people like my size, you know, I hit 75 degrees just by rolling over, but that's not the point. So you can see this very narrow field that we have with the relative humidity, with air movement and surface temperature and air quality, the acoustics, even the lighting quantity is an issue. Even security can be an issue. But again, it's our very narrow little field zone of comfort, okay? And then when we get into vapor pressure and building codes, again, like I said before, we're getting into where engineers have literally will put on the blueprints how much of the vapor pressure is during each part of the year from the earth, from the air, and from the sun itself. And it's based on the year before. So the contractor putting this poor building together is got to know what they're doing while they're there. They may change phases of putting the building together so that they can protect the drywall that's inside the building or the honey board that goes on the exterior or a wrap on the building. And like here in the US, and I'm not sure about other parts of the world, but like here in the US, we have pretty much like three walls, right? One wall, we have a wrap on the exterior of the studs, and that's typically in our summer climates, our hotter climates because of the HVAC systems and keeping the environment from outside coming in. And then on the colder side of the environment, like in the Northeast and up to say from about Washington, DC to all the way over to Colorado and all that, all the way up to Maine, we have it on the inside of our studs so that we keep the temperature in the environment inside so that we don't have a cold environment when we're in our homes. And then we have where in the southern, Southern California, all the way to Texas, and even into Florida, parts of those areas, they don't have any kind of that wrap. They have building wrap, but not that kind of wrap. It's not a vapor retarding wrap. And so we have to know these things when we are drying a building, because we may have to remove drywall so that we can dry out the insulation or just remove the insulation. And we need to be aware of those environments that are being produced and how that is being brought in with the vapor codes and how the contractor is building things for us. Now, earlier, I mentioned how easy it is to understand vapor pressure, right? And so if you were to throw a 70 degrees, 80 degrees, and were to go up, you got your dry bulb, right? And we know it's your dry bulb because of what is being down, what's down on the bottom of the psychrometric chart. And then if you follow the blue line, it'll take you from the dew point all the way over, and that gives you your dew point readings. But where the dew point, I'm sorry, where the dry bulb and the wet bulb meet is a key, because it is a key to everything. Right then and there, you can get your relative humidity, you can get your vapor pressure, all of your stuff, all of your readings right then and there. And that's what's so unique about these two elements. Now, just to be clear, the dry bulb temperature is defined as a temperature of air measured by a thermometer. And when you use a thermometer, use one that is quality and one that is accurate. It's important that you use that an accurate device that freely. So by using a thermometer freely exposed to the air, but shield from radiation and moisture. And we understand what that means, right? You can't put it on top of something and collect your readings, right? Because that, whatever you put it on is going to give you a false reading. You can't set it off to the side where it's drawing in the environment like that, because it's not. You've got to hold it, whether you put it on a tripod or whether you hold it in your hand, but it needs to acclimate to the environment, and you need to be able to know that it's an accurate device, right? Then the wet bulb temperature is the lowest temperature that can be achieved solely through the evaporation of the water. Now, the comparison of a dry bulb and a wet bulb temperature forms the fundamental basis of all environmental thermodynamics consideration, right? Vapor pressure as a whole is so that we all understand, right? We're all on the same sheet. Is the vapor pressure is exerted by the vapor in thermodynamic equilibrium with condensed phases, solid or liquid, in a closed container. So what is a vapor pressure? The definition is result law formula. You can look that up. Vapor pressure, the strategy behind it as a drying process is effective drying strategy by allowing you to not only monitor the environment in the air, but you're mainly focusing on the material. And while you're doing that, you also can go to your dehumidifier and you can confirm your dehumidifiers are working to expectations by understanding the grains per pounds, right? So that is another part that we need to understand when we're talking about vapor pressure and the driving forces behind all that moisture phase changes. When there is a difference in the vapor pressure, nature will seek to equilibrium, right? So we know that when we come to a drying loss, if we simply open up the door and put a fan there, it will draw out the greater amount of moisture because it's seeking equilibrium, right? And we know this because you can put a hole in a balloon, or I don't know, you can figure it out, and a hole in a tire. I mean, there's multiple ways to show examples, right? But the principle is the analogous to the behavior observed when a hole is made, and that the pressure inside will always move towards that lower pressure outside. So we need to understand that. And while the concept of vapor pressure may seem straightforward, and calculating this pressure requires little understanding, but it requires a huge understanding when you're applying it to construction materials and stuff like that. So here we're talking about the water vapor pressure at 0.15 and the water vapor pressure, right? And typically water vapor and vapor pressure or water vapor pressure is all the same thing. It's just depending on how the author wants to use the words and they're at their discretions. So the moisture level in the air is expressed as a percentage of the maximum amount of moisture the air can hold, right? And we can take a look at that and say, for instance, if the dry bulb is 70 and the wet bulb temperature is 63, the air is only able to hold 50% of its maximum moisture capacity, which is at 77 Fahrenheit. So we now know how much moisture that air can hold, which is important when we are coming up with a drying plan or a drying, what do they call it now? A remediation work plan. So, but yeah. I mean, here, this is about sensible heat. And we need to understand sensible heat because of how it plays within enthalpy, right? So the heat that causes a change in temperature measured in joules per kilograms is latent heat. And that heat that causes a change in state without a change, how do you want to say it, it's in the temperature measured in the joules per kilograms, right? And for the example here, what I did was I took the latent cool that equaled 19 and the sensible cooling at 22. And then I noted that the 1.0 joules equaled 1 point and the watts was 1.1 kilowatts. So I already know what's going on within my environment, and I know how much my equipment is putting out there to add the sensible heat based on the motors and the engines within those devices, right? Now, this is kind of like another example of a building's comfortability. As you can see, it talks about the warm and dry environments, the cool and humid. It's letting us know when we are adding moisture, when we're drying, we're cooling, and we're warming. This is important so that when we go into that environment, we know that the internal vapor pressure and the HVAC system that's controlling the indoor environment is working in this format. And we need to know that so that we understand how to set up a program to initiate the drying and stuff like that. The basics to vapor pressure are essential for structural drying. And you notice that during our advanced structural drawings, we talked about vapor pressure, right? And there's a lot of great equipment out there that can help us. Obviously, our moisture meters are the primary factors, right? Nanometers, thermometers are all great tools for this work. And they can trap and capture the imaging for dehumidifiers, air movers, and how the psychometric is working out within our drying structure. And it can quickly and effectively prevent long-term damage, which is truly, as a restorer, you don't ever want, or a cleaner, you don't ever want to be the one that causes long-term permanent damage, right? But anyhow, preventing long-term damage, right? Air movers should be set. Now, the industry standards is that they give us a basis to what we need to do to start getting the environment under control and stabilization. Now, the industry doesn't tell us how to do the rest. They give us an idea how to do the rest of the air mover setup, but a lot of it has got to be set up by the restorer and not by anybody else, because it's the restorer who is the subject matter expert in drying these buildings, these environments. And that's why they're there. That's why they have a job. That's what they do. Nobody else can do, right? They can control the humidity, and the temperature, and the ventilations is in the ventilation from the HVAC system, or opening up the building to burp it and do all these other things. But they know the restorer, the cleaner, have to be always brought into the discussion on how to set up the equipment and how to use the tools to create these drying environments, right? And then what I did here was I showed you the value of moisture removal by condensation during drying, and how it refers to the amount of water vapor converted into a liquid and subsequently removed from that environment. This process is crucial in structural drying, as it helps to reduce the overall moisture contents in the building materials, preventing issues like we discussed, wood damage or mold growth and bacteria and malodors and stuff like that. Now, then we went into additional information about equipment and the actual technology, right? And we all know about desiccants, we all know about LGRs, and we, I just drew a blank to the other one, but I'll get to it. I always will. But anyhow, the overview of our latest drying equipment and technology is astronomical, right? We now have Bluetooth on our equipment that we can be at home and it's telling us what's going on with our equipment. We have devices that we can plug in that can tell us what's going on with the environment, provided no one moved them or done anything with them, right? And then we got, our air movers are getting better, because now we have air movers that have HEPA filters. You can screw them to the top of that, and you can introduce them to different environments, and you don't have to worry about kicking up that particulate and they just going flying everywhere. It gets kicked up, it gets collected up by that filter, and that's a great thing. And then getting out there about the cyclometric tool, right? Discussing how that cyclometric thing works is another thing that's coming out, and we as an industry need to understand. And how the equipment is designed influences what we're doing today, right? It's all important that we understand that the airflow designs, the heat distribution, the materials that are handling and retaining moisture, and what their reaction is to all of this stuff, right? And another unique thing that's come up with our equipment is that they have become more and more energy efficient for managing vapor pressure in large scale operations. Recovery systems, and what we understand is the heat recovery system is usually, like I said, also release the heat to materials, right? To heat and stuff like that, right? And so we have an understanding of all that. And then we talk about, how the drying stages are being impacted by what we talk technology. I mean, can you imagine it? You're sitting at home and your phone pings and you look down at your phone and you've hit all your material drying fills, i.e. they are now in drying phase, or they are in one of the two falling stages. What does that tell you? That tells you a lot, because now you can see how things are going on in your job. You know what phase and what stage you're in your job. You also know how your equipment is going to be working. So if you have a dehumidifier that isn't working or it doesn't need to be on the project, you can remove it, right? if you have control and stabilization of the environment, you still need all of that dehumidifiers. Do you still need all those desiccants? Do you still need all those air movers? Now we can reevaluate that environment before we go into the drying phase, before we go into the two unique phases and stages of drying. So there's a lot for us now out there, and it's going to continue to get better and better because we are investing a lot of time and science from the companies and companies that use this equipment and discussing with the manufacturers who build this equipment, right? So then we talk about air movers and stuff like that, and how the air is taken into them, right? We always got to remember one key factor in the science, and that is that air movers, it doesn't matter what it put, if it produces air in two forms, uncontrolled or controlled. And we know the difference because controlled is just a lay flats over the outport, and it delivers it to where we want it to be and at a control measure, whether we put half cuts inside there and it releases it as it goes along the pipe of a lay flex, or it's uncontrolled and it's just blowing everywhere within the room. And these are the things that are very important to understand when it comes to the air movers, because we have to understand that the air movers themselves are probably one of the greatest assets that we have for drying a structure until we hit that point of free, and then we go into bound water, and we have to understand all of that, right? So we need to understand air movers and how they deliver their energy to our projects and to our environments. It's key, okay? Then I went into discussing the dehumidifiers. And again, like I said before, dehumidifiers, they create air, right? And so those airs, just like the AFD's air, all create air. And so it has to be either controlled or it has to be open, and it has to be put in a way that it does not bring up a lot of particulates, a lot of disruption for the environments and the people that are working in that area, as well as our people that are doing the work in that area. And we talk about the effectiveness of the dehumidifier involves measuring the environment that's coming in and the environment that's going out. That gives us so much about our dehumidifiers. And I've seen this time and time again. People will tell their clients, well, this is going to collect this much pints for 24 hours or this many gallons for the next 24 hours. In reality, it has no value. The true value of a dehumidifier is being able to know what the difference is, so you understand how that dehumidifier is working. You need to understand what's going in, what's going out, and what the difference is, so that you understand how much of your dehumidifier is truly working. Once you understand that information, the vapor pressure, and you apply the vapor pressure, then you realize how effective your drying environment is and how effective the equipment is in assisting you as the cleaner or the restorer, because no one can dry an environment like you. That's what you're paid to do. And then but yeah, the dehumidifiers need to be understood, right? At this point, I have an interactive Q&A session. So I know this is a pre-recording, so it's an open floor to questions in the sense that if you want to send me information or discuss with me, you can. What I've done is put my information here. You're more than welcome to contact me here, and I'll answer your questions about vapor pressure. And then we can go from there, so that we can discuss whatever it is that you want. I'd like to be able to do is with your questions, I'll leave it anonymous, but I'd like to see if I can work it out that we post them with our host, and so that other people can see your questions and they can learn from them. Okay.
Thanks so much, Josh. That was fantastic. Yes, we can definitely do that. We can definitely make them available so everybody can see as well. Yep, perfect. Yeah, thank you. That was really informative. So much science behind the madness too. It's quite in-depth and very interesting. Yeah, perfect. So definitely, if any viewers that are watching this when it's available, there's the contact details for Josh in this presentation, so you'll be able to pick those up. If you do want to get in contact with him, definitely reach out. He's more than happy to help you with any questions. Perfect. Other than that, as it is pre-recorded and it will be released in a couple of days, we don't actually have the interactive, but definitely get in touch with Josh if you do want to reach out. Other than that, we'll wrap it up from there. So I'll stop recording. Thank you very much. And anyone who's watching afterwards, hopefully you do enjoy this, and yep, definitely reach out. Thank you so much. Thank you.
You're welcome.